Welcome to Engineering Studio with Dr. Mohammad Tahir. In this video, we are going to solve one example related to the design of beam with compression flange laterally braced at reaction points only. Design the beam of figure with the lateral bracing only provided at the reaction point. So we are given with the simply supported beam having span 3.5 plus 3.5 7 meter span and subjected to uniformly distributed dead and live load throughout the span and point loads of 60 kN dead and 50 kN live at the center of the span. The compression flange is laterally supported only at the reaction points. In between, there is no lateral support provided for the lateral torsional buckling. We are supposed to design this simply supported beam by using compact I section. So first of all, we need to estimate the self weight of the beam. So in the case when the superimposed dead load is given, so we can take the 10% of the dead load as a self weight of the beam. So in this case, the dead load in the form of uniformly distributed as well as point load is given. So the 10% of uniformly distributed dead load and the 10% of point load distributed over the entire length. So here 60 is the point load which is acting at the center, and we need to distribute it over the entire length to convert it into load per unit length. So the self weight will become 1.7 kN per meter. After calculating the self weight, we need to calculate the factor load. So here, as the two different type of loading are acting on the beam, uniformly distributed and point load, so we can calculate the factor load separately for uniformly distributed load and point load. So 1.2 times the uniformly distributed load, and this self weight will be considered in the uniformly distributed load because self weight act over the entire length of the beam. So 1.2 times dead load and 1.6 times live load, so it will give us the factored uniformly distributed load. And similarly, we need to calculate the factored point load. So it is 1.2 times 60, the dead load, superimposed dead load, plus 1.6 times superimposed live load, so it is 152 kilonewton. So after that, we need to calculate the bending moment and shear force diagram based on the factor load. So now the factor load is WU, uniformly distributed load 27.64, and point load is 152 kilonewton. So we can calculate the reaction at this support. So the reaction at the support will be equal to PU divided by 2 plus WU into L divided by 2, and it comes out to be 172.74 kilonewton. So after that, we can calculate, or we can draw the shear force diagram. So 172.74 at this point, and then it will be continuously decreasing linearly because of this UDL, and then it will decrease by 152 kilonewton at this point where the point load is acting, and then again it will be decreasing by this WU, and at the end again it will be 172.74. So after that, we can draw the bending moment diagram. So as two different type of loading are acting on the beam, so we can draw the bending moment diagram separately for these two loads. So we can draw the bending moment by parts. For uniformly distributed load, the maximum ordinate will be WL square by 8, and here it will be PL by 4. So after constructing these bending moment diagram, if we want to calculate the bending moment at any point, for example at the center, so we can simply add up these two values, 266 kilonewton meter and 169.3 kilonewton. And if we want to calculate the bending moment at any intermediate point, so in that case just calculate this ordinate and then simply sum up these two values. So after drawing the shear force and bending moment diagram, the next step is to calculate the CB value. So to calculate the CB value, we need the M maximum in the span, MA, MB and MC. MA will be at 1/4 of the span, MB will be at the center, and MC will be at 3/4 of the span. So in our case, as the loading is symmetrical, so M maximum will be equal to MB and MA will be equal to MC. So we can estimate their values by using these bending moment diagrams. So the M maximum will be the sum of these 169 0.3 plus 266. So we can calculate the maximum bending moment, M maximum, and it will be equal to MB, moment at the center. And to calculate the moment at this 1/4 point, mean half of this 3.5 meter, 1 point at the location of 1.75 meter on this side, similarly on this side. So for that we can calculate it by MA is equal to 172.74 multiplied by this distance 1.75 minus this W times, mean W 27.64 times this span, which is 1.75 square divided by 2. So from here we can calculate the MA value, and it will be equal to MC. So the calculated value of MB or M maximum is 435.3 kilonewton meter. MA and MC will be equal to 259.97 kilonewton meter. So once we have these 4 moment values, so we can calculate the CB value by substituting the values in this expression. So it comes out to be 1.24. So here this 6.5 value is actually 2.5 plus 4. 2.5 plus 4, it is 6.5. And similarly this 6 factor is actually 3 plus 3, because MA and MC are equal. So we can add up these two values. So it will be 6 times 259.97 mean MA or MC. So the CB is 1.24. So after calculating the CB value, we need to enlist the maximum bending moment, maximum shear force, and the unbraced length. So in our case, as there is no intermediate lateral support, so the unsupported length will be equal to the complete span 7 meter. So by assuming that the section is internally compact and there is no lateral torsional buckling, we can calculate the required section modulus MU divided by phi Fy, and MU is the M maximum and Fy is 250, so it comes out to be 1935 into 10 raised to power 3. Similarly, we need to calculate D minimum to select the section. For buildings it is L over 22 and L is 7 meter, so the D minimum comes out to be 318 millimeter. So based on this ZX and D minimum, we need to select the section having the minimum weight. So we can use the selection tables to calculate the select the required section. So considering this ZX required, so it is 1935, so its value is close to this one. So we can select this section 310 into 117. But as we know, in each group, the section at the top of the group will be the most economical section. So we can select this 610 by 82. And the D minimum for this section is 599, which is considerably larger than this 318 value. So after selecting the section from this table, now we can write that our trial section is 610 into 82, and we can select the values, these properties of the section from this table. For example, the MP for this section is 494 and MR is 295, LP is 1.69, LR is 5.10 and BF is 65.0. So here phi B MP is 494. So here if we see MP is 549. So actually phi B MP is equal to 494, and if I calculate MP, it will be 494 divided by phi B, which is 0.9. So it comes out to be 549. So this is actually the MP value after dividing the factor phi B. Similarly, MR after dividing the factor phi B. And BF is 64, LR 5.10 and LP 1.67. So we can select all these values from that table. So as in this case CB is more than 1, so we need to consider LM instead of LP. So we need to calculate this LM value, which is LP plus MP over BF, CB minus 1 over CB. So it comes out to be 3.33 meter. So as LB is greater than LM, LB is 7 meter in this case, and it is significantly higher than this 3.33 meter. So in that case, we cannot use the beam selection tables. So we need to go for the beam selection charts, because if LB is more than LM of the section which is selected based on the beam selection table, so the selected section will not be suitable in this case. So we need to reselect the section based on the beam selection charts. And to select the section based on this beam selection chart, we need LB value and M value. And if CB is more than 1, so we need to divide this M maximum by CB to get the M equivalent. So the M maximum is 435. We need to divide it with CB 1.24 to get the M equivalent, which is 351.05. And now we can select the section based on this unbraced length and based on this bending moment from the beam selection charts. So here is this beam selection chart. We need to enter in this chart based on this unbraced length, which is 7 meter, and the moment is 351. So based on this, the point will be over here, and we need to move in the upward direction and right direction, and the first line encountered will be our required section. But here the first line is a dotted line, and if the first line or the encountered line is a dotted line, so that will not be an economical section. So if we want an economical section, so any solid line on the right side will be our required section. So now our selection will be 410 by 100, 410 by 100, W 410 by 100, because the section corresponding to this dotted line will not be economical. The section corresponding to this solid line will be economical. Okay, so from here, from this beam selection chart, we can see this selected section, which is 410 by 100, and we can select its properties MP, MR, LP, LR, BF, D, and then we can again calculate the LM value. So here our trial section is 410 by 100. So first we need to check whether our selected section is compact or not. So for that we need to see these three conditions. The first condition is web is continuously connected with the flange, and this is okay because in case of hot rolled section, the web is continuously connected with the flanges. And then we need to calculate BF over 2TF and H over TW. We can calculate these values based on the properties, mean width of the flange, thickness of the flange, H, and TW, thickness of the web, for the selected section, or we can select these values from this table. We can see over here H over TW, so we can select these values from over here. So the values are 7.7 and 35.9, and we need to compare it with the lambda P, and lambda P for HW. So lambda P for A36 steel will be 10.8 for flanges and 107 for web. So you can refer to the previous video for example 1, and if we compare it with the BF over 2TF and H over TW of our selected section, so both the conditions are okay. So we can say that our section is internally compact. So after that, again we need to calculate this LM value because CB is more than 1. So for that, LM is equal to LP plus MP over BF, CB 1 over CB. So again we can select these values from the beam selection table, and here LP is equal to 3.1, LR is 10, BF is 28.53 for our selected section, and MP is 532. In the table the value is given 5B MP, and if we want to calculate MP, so it will be the 5B MP value, for example it is X, so X divided by 5B, so it comes out to be 532.5 kilonewton meter. Okay, so by substituting these values, LM will become 6.72 meter. So now to calculate the flexural capacity of the member, we need to compare our unbraced length with the limiting value of unbraced length LM and LR. So 7 meter is more than this 6.72 meter and it is less than this 10 meter LR. So it means we are in the inelastic lateral torsional buckling case. So if the buckling is inelastic, so in that case we can use this expression to calculate the bending moment capacity. So we are in this range, So for this range we can calculate the moment capacity by using this expression. So CB 0.9, MP 532, BF 28.53 and LB is 7 and LP is 3.11. So we can also select its value, which is 3.11 over here. So the 5B Mn value comes out to be 470.44 kilonewton meter. So this is the flexural capacity of the member corresponding to inelastic lateral torsional buckling. So now we need to compare the capacity 5B Mn with the applied bending moment, which is 435.4 kilonewton meter. So this 470 is more than this 435, so it means okay, our selected section has sufficient capacity to resist the applied bending moment. Okay, after that we need to apply the shear check, and for that we need to see that whether H over TW, which is 35.9 for our selected section, it should be less than 63.4, and this 63.4 is again 2.42. There is a factor like this, E over Fy. So you can refer to the previous video related to the example 1 for that, and for Fy 250 its value comes out to be 63.4. So when this H over TW is less than 63.4, so in that case the CV will be equal to 1. We can use the limit corresponding to the yielding of the web for shear capacity of the section. So here the shear capacity will be equal to 5V, which is 0.9, and Vn is equal to 0.6 times Fy area of web times CV, and divided by 1000 to convert it into kilonewton. So 0.9 into 0.6 divided by 1000 into 250 Fy. This area of web is equal to D into T. So total depth of the section, which is 415, and thickness of the web is 10 millimeter, and CV is 1. So the 5Vn comes out to be 560.25 kilonewton, and the applied shear is 172.74 kilonewton. So the design capacity of the section is significantly higher than the applied shear value. So it means our section is adequate to resist the applied shear. After that we need to apply the deflection check. For that we can calculate the actual deflection. So in our case we are having two different type of loading, mean uniformly distributed load and point load. So for that we can calculate the deflection separately for uniformly distributed load and point load. So the formulas are given over here. So this formula is for uniformly distributed load 5 over 384 WL into L raised to power EI. Here WL is uniformly distributed live load, and similarly for point live load the formula is Px over 48 EI 3L square minus 4x square, and if we take this 4 common out of this expression, so it will become Px over 12 into 0.75 L square minus x square. Okay, so we can substitute the values in these two expression to calculate the delta actual. So 5 over 384 into WL, which is 10, and L mean the span is 7 meter raised to power 4, E is 200,000, and I we can select from the properties table for our selected section, which is 39700 into 10 raised to power 4. And similarly for point load it will be equal to P, which is 50 kilonewton. So we need to convert it into newton. So 50,000 into span x, mean this point load is acting at the center, so x will be 3.5, and divided by 12 times E times I, and here 0.75 mean 3 divided by 4, and then span square minus x square, mean the point at which the point load is acting. So after substituting these values the deflection because of uniformly distributed load is 3.94 and deflection because of point load is 4.5 millimeter. So the total deflection is 8.44 millimeter, and the allowable deflection in case of buildings is L over 360, which comes out to be 19.44 for a 7 meter long beam. So the delta actual, which is 8.44, is less than the allowable limit L over 360. So it means our deflection check is also satisfied. After that, we need to check for the self weight, that the actual self weight should be less than the assumed self weight, or it should be less than 1.2 times the assumed self weight. So the actual self weight is 100 kilogram per meter. To convert it into kilonewton, we need to multiply it with 9.81 and divide by 1000. So it comes out to be 0.981 kilonewton per meter, and it is less than 1.7 kilonewton, which is the assumed self weight. So it means the self weight check is also okay. Otherwise, if this is more than this value 1.79, we need to redesign the section based on the new assumed load. So our final selection will be 410 by 100.